This vast land mass was surrounded by a deep ocean trench. And from this trench, rock plates which had formed the continent dropped slowly toward the Earth's core. This resulted in a surge of heated rock towards the crust. The plume is forced up until it breaks the surface in a massive eruption, a dome of lava rising from the center of the Earth. Thus, the first cause of the mass extinction came from within. Although this was an eruption on an unprecedented scale, it was still localized. This alone could not have wiped out most of life on Earth, but perhaps it was the trigger. All life in the immediate vicinity would have been wiped out, but not across the globe. Some other factor must have been in play. Evidence came from drilling in the deep ocean off Japan in 2002. The offshore survey is searching for methane hydrate, which could become an alternative energy source. Methane hydrate is a unique substance formed when water and methane gas bond together. When buried deep beneath the ocean, it is frozen. Deep in the seabed, where the temperature is always low, methane hydrate is very stable. Once the temperature rises, it melts and generates methane gas in volumes over 150 times larger than when the gas was bonded. It is very volatile. In China, at the boundary that marks the mass extinction, evidence was found that large amounts of methane hydrate had started to melt at the same time as the Siberian eruption. And also, there was a dramatic increase in an element called carbon-12. Methane hydrate also contains high levels of carbon-12. The two had to be connected. But perhaps methane hydrate was the culprit which caused the mass extinction. Dr. Paul Wignall of the University of Leeds in Great Britain is certain that methane hydrate was one of the culprits.
Now, of course, ice melts, and in fact, we know from the present-day methane hydrates, which are trapped beneath the sediment, that it would only take a temperature rise of the waters of a few degrees, and then we would start melting that ice, and as the ice melts, it will release its methane, which will bubble out to the ocean surface, and then, hey presto, you've got a nasty greenhouse gas escaping. And we think that this melting of methane hydrates may have happened at the end of the Permian.
There is always cause and effect. This volcanic eruption released huge quantities of carbon dioxide, which then caused the Earth's temperature to climb. As the water temperature rose, methane hydrate began to melt. Methane is 20 times more efficient as a greenhouse gas than carbon dioxide. Global temperatures soared, thus releasing even more methane hydrate.
We get a positive feedback. The release of the methane will accelerate the increase of warming, which will release more methane, which will accelerate more and more the global warming, until eventually you have this catastrophic increase. It's a sort of a super greenhouse climate, probably the hottest that the planet has been for the past sort of 600 million years or so.
Once started, the process is hard to stop. At the equator, temperatures rose by several degrees, but at the poles, by a massive 25 Celsius, almost 80 degrees Fahrenheit. And this had a devastating effect around the globe. Entire ecosystems vanished. And if this wasn't bad enough, oxygen levels dropped. This was the critical element of extinction, triggered by the volcanic eruption. And the firm evidence of that can be found in the frozen continent of Antarctica. Amidst the exposed rocks of the Transantarctic mountain range, researchers from the USA and South Africa pool their resources. Dr. Greg Ritalik of the University of Oregon is team leader. He has detected a very rare mineral locked in the rock strata, which immediately followed the mass extinction.
In this part of the sequence that's exposed here, in the very early Triassic, we have some really unusual soils. I've not seen anything like them anywhere else but in this particular early Triassic zone of death. Here's one here. Top of it's there. Root traces go down to this unusual nodule here. It's a very weird mineral called berthierine, and it indicates very low oxygen conditions in the early Triassic.
The mineral berthierine cannot be produced when oxygen is abundant. The discovery of this mineral is added proof that the world had undergone great change. It would have been hot, and the animals that depended upon oxygen would have suffocated. Dr. Bob Berner of Yale University fed data based on different geological findings into a computer. This is his result. Oxygen levels today are about 20%. Just before the mass extinction, oxygen levels had risen to around 30%. Then it plummeted to 10%. Several factors were at work. When the plants died out, they stopped producing oxygen, and methane gas released from the seabed reacted with oxygen molecules, considerably reducing the atmospheric levels. Some animals managed to survive. One of them was the creature we think is our common ancestor, Cynodont. That it survived at all is probably due to chance and luck. Yet this oxygen-depleted climate allowed a species of reptile to dominate all life on the miracle planet.